Hi guys, let's continue. We've got RC circuits is our next thing that we're going to do. Keep in mind, I drew an RC circuit for us here. Keep in mind we're charging the capacitor initially. Okay, we're going to go through the discharge of the capacitor in a little bit, but we're initially charging the capacitor. We've got our capacitor here, the resistor. Whoa. Sorry about that. The resistor is a frictional component to this situation. We start out at 0 equals Q, and we're going to go to Q equals Q max. And we can use the book's terminology or nomenclature for Q max as Q. That's fine. We're going to apply the loop rule. Okay, so I'm going to do it for you in a second. We're going to go from point A. So we're going to start here. We're going to go through our loop all the way back to point A. Okay, so how do we do our loop rule? This is it right here for this equation. We're going to subtract off IR, okay, because our current, if you notice right here, our current is going with our loop. So that means it's a voltage drop, IR. We're going to have a voltage drop across the capacitor. So negative voltage across the capacitor. And then we're going to add, because we're going from negative to positive across our EMF. We're going to say that equals to 0. That's our loop rule. Well, this is nothing more than a first order differential equation, okay? First order diffie Q. Let's rewrite it as R times dQ dt minus Q over C. So here's a few things. We know that dQ dt is I, and we know that the voltage across the capacitor, this guy right here, the voltage across the capacitor is our Q at any given amount of time, QT, divided by our capacitance. Okay? And that's what we're wanting to get. We want to get this QT, this function of Q as a function of T. That's what we want. Okay? Now, after T goes to infinity or some really large amount, we're going to have a full Q there. Okay, that'll be our Q max. The voltage across it will be our voltage epsilon, and if you divide Q max by the capacitance, we're going to have our total. Okay, so that's going to be useful later. So now we've got this first order differential equation. What do we want? Free food. How are we going to get it? Oh, I don't know. We want this, dt over RC. All right. Why do we want it that way? Because we're going to do an integral. Okay, that's why. And if we get dt over RC, because of the nature of our equation, we're going to solve for dq dt first. And the nature of that equation, solving for dq dt, is going to give us some things. And dt will be on the top on one side of the equation. dq will be on the top on the other side of the equation, in the numerators, I should say, right and left-hand side. If we can do this right. So we do this chain, and we end up with dq dt is equal to this bit right here, okay? We can then quickly go to here, and we've got our capacitance times our EMF minus Q over dQ, RC over dt. So we're almost there. We almost have dt over RC, and all we need to do is invert both sides, and then we can start integrating. So we've inverted both sides. We can start integrating 0 to Q, and we're going to go to 0 to some t on the dt side. Okay? Well, I'm not going to do all the integration for this integral. I'm not going to do the algebra. But you do the integral, okay? You set your u equals c like that. You do your du, dq, and all that other stuff. Anyway, you figure out what dq is. You put it in. You do all those things. You figure out what 0 is with respect to u and q is with respect to u and blah, blah, blah. Anyway, you'll get it. And this is the result. So we have this result after our logarithm. We now can turn this equation, follow the arrow, and we get q of t equals c times epsilon, our EMF, times 1 minus this. Okay? Well, first of all, our time constant is RC, right? You can see clearly the time constant is RC. And from up above, we already said that our Q is equal to our capacitance times the EMF. So our capacitance times the EMF gives us our Q, and we can put our time constant in right there, tau. All right. Sweet as punch. So we have this Q of t, all right? That's nice, right? It's a really helpful thing because now we can start looking at our current. You know what? Before we do, let's do a thing. Let's ask ourselves about this right here. Okay, which is really e to the minus t over tau. And what happens when t equals tau? Well, then we've got e to the minus 1. And e to the minus 1 is equal to 0.368. 1 minus e to the minus 1. Well, that's just 1 minus that. And so that's 0.632. Okay? So if we are at a point where our time has gone for exactly one time constant, then our qt is equal to q times 0.632. All right? Good. We're going to talk about the other one in a second, but I just want to I wanted to do that. Okay. Now, what do we get when we want the current for this situation? We want I as a function of t, but we know that I is just dq dt. So we can take the derivative of I with respect to t. Cake, it's not difficult at all. And you end up with e over r e to the minus t over tau. Well, you can rewrite that because V equals IR. You got to remember your EMF is a voltage, okay? So we get our I naught E, oh, I already did E. You don't need e's twice. E to the minus t over tau. And we're done. Now, this was all charging, okay? So that was charging the capacitor. Now we're going to discharge the capacitor. So discharging the capacitor, what do we have? We've got essentially a capacitor, let's just draw it out, and a resistor. Okay, we're no longer connected to an EMF. We no longer have a driving EMF that's charging the capacitor. We're just letting the capacitor discharge across some resistance load. All right, so we can do the same thing, and we can do our loop rule if we want to. And our loop rule will tell us, we can call it loop 1, even though there are no other loops. But okay, so let's do it. We've got loop 1 is going through with the same current flow. So we can do our current, which is dq dt times R, and we're going to drop our voltage across there, and that equals 0. Well, we can just make this positive and this positive and rewrite it as dq dt times R is equal to R minus Q over C. So far, so good. Now, it's easy to see that we can do dt over RC. That's a quick and easy one. And that's going to equal, what do we have? Boom, boom, boom. dq over q. And we're going to, one of them has to be negative. So we'll make the dq side the negative side. Then we're left with, we want to go from 0 to some t. 0 to some t, 1 over tau, okay, because tau is still going to equal RC. So we're going to tau, and we've got dt here, and we're going to do negative 0 to q of dq over q. All right. I don't know. I think you guys can, what am I doing? I think you guys can do that integral. I believe in you. So I'm going to simply write out this as our Q on the capacitor as a function of time. So this is Q on the capacitor as a function of time when discharging Okay, so we're discharging the capacitor. This is it. What is our current? Our dq dt is our current. And we can write that as negative q over rc times e to the minus t over tau. And I wrote tau as rc because we want to know what I max is, and that's q over rc. Okay, so our it as a function of time is going to be negative q over, oh gosh, why am I rewriting negative q? Negative I max e to the minus t over tau. All right, so good for us. Lastly, we want the voltages across the resistor and the capacitor. So we want, we just want them. We want to know what those are as a function of time. So let's do it. Let's go back to charging the capacitor. So we're charging the capacitor. I should have done those before I moved to discharging the capacitor, I suppose. So we're back to charging the capacitor. And we definitely want the voltage across the resistor as a function of time. So we want that. That's a question of ours. And we want the voltage of the capacitor as a function of time. So both of those, we're curious. We want to know what those things are. So, fine. Let's go back to our first order differential equation. And let's rewrite it. Or let's rewrite an equation. We know that the voltage across the resistor plus the voltage across the capacitor is going to equal the EMF, okay? And we know that V equals IR. So our I max times R is going to be that EMF, okay? So, awesome. So far, so good. V of R is easy because, again, Ohm's law. So VR of t is equal to our R times I of t. That's so easy I can't even stand it. We just do I max times R and e to the minus t over tau. So simple. That's going to go in there. And what do you know? That's what that was, right? So nice for us. What does this really equate to? IR, well, that's just nothing but our epsilon, our EMF times e to the minus t over tau. So I'm going to rewrite this over here on this side so we can box it in nice and clean. What is VC as a function of time? Well, here's a nice little trick. we can take this equation right here. Let's just take this part of the equation. And we just say VC of t equals our EMF minus our V of R as a function of time. So if we write that out, we've got our EMF minus EMF times e to the minus t over tau. Factor out the EMF, and we've got 1 minus e to the minus t over tau. And we now have both of our equations that we were looking to get. Okay, when we're charging the capacitor, we said we're charging the capacitor, we want to know this, and we want to know that. And we went back to our differential equation, and we got those things, right? Here's the first one, and here's the second one. Okay, so what's our next move? Our next move would be, well, maybe your next move. Your next move. What are they when discharging? The capacitor. And I'm not going to do it. I'm going to leave that to you guys. What are they when discharging? I have to make a note for a second here. Okay, thank you. Skip, right? All you had to do was skip that bit. And we are back on our journey to learn about magnetic fields and circuits and all the stuff. Oh, heck. There's no way to pause this, I don't think, but I'd like to pause. But I don't see a pause in our future. Maybe we should. Pause. Let's take a break, and we'll come back for whatever's next, because I'm not 100% sure what we're going to be doing next. Okay.